I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
Okay, Jam, are you ready for our topic today?
I think so. Let me check. Yeah, I'm ready.
So we're going to be talking about how odor absorbers work.
Okay. Interesting. Like the ones you put in your shoes or?
I actually like the ones
in the
you
fridge?
spray in Febreze.
Oh, okay. Gotcha.
So this is a specific type of odor absorbers. I want to do the kind like you put in your shoes at some point, but this one I think works differently.
Well, in terms of like usage in my life, I've definitely used Febreze 100,000 times more than I've used the shoe ones. I'll tell you that much.
Well, interestingly, this episode was inspired because I have the ones that you put in your shoes for my ice skates.
Oh, nice.
And I was talking to my friend Amber and I was saying, I wonder how these work.
Mm-hmm.
And then I decided to dive into it. But I found this other one about Febreze much quicker and easier. And I was very excited by it. So I switched gears. So
Nice.
And the other reason I was excited by it is because a long time ago, I was listening to an audiobook, which I think was about habits. And they talked about how originally Febreze was a super effective odor eliminator with no replacement smell. It was just the odor eliminator. And they added in the artificial smells because of something about the habits that people had. And the original product didn't sell very well at all. Once they added in the artificial smells, it flew off the shelf.
Weird.
And that blew my mind because to that point, I had always thought that Febreze was just covering up smells. But actually, it's not. And from that moment on, I wanted to know what the chemistry was.
Yeah.
And that's how I got started down this path. Okay.
That's interesting. I wish I could kind of get a hold of the old one, like the just eliminator one, to not have a replacement smell. I get why people want the one that replaces it with another smell. But just for my curiosity, I'd love to see how something like that works and test it on stuff to see where it'd be like, okay, there was a smell and now there's not, you know?
I did go to the Febreze website to see if I could find that. And it seems like they now have one with no artificial scents, and I want to try it.
Nice.
It might be that they had to use the other ones to get popular, and now they're bringing back the original because they can.
Yeah, they might have been ahead of their time a little bit because people now might be like way into that. And in the 90s or whenever that was, people were not. They're like, I'm sorry, I want things to smell good, not just not bad. Thank you.
Exactly.
I have a distinct memory of Febreze like getting big in the 90s, like very distinct memory. I don't know why that stuck with me. Like I was not worried about cleaning house whenever I was a kiddo, and the smells of things. In fact, I was contributing to the opposite most of the time, I'm sure. But I have a distinct memory of the Febreze commercials coming out of nowhere. Just so many commercials out of nowhere.
Well, I really don't like the smell of Febreze replacement smell, so I would be so into this. Okay, so let's go all the way back to when we learned about smell, which I think we talked about that in the episode about why things smell bad. So we talked about how we have olfactory receptors. Jim, you called it the olfactory.
Oh, yeah. The good olfactory.
So we have molecules that are able to vaporize, and those molecules, the vaporized molecules, the ones that turn into gaseous molecules, come up and hit our nose and hit our odor receptors. And that's how we smell things. And the odor receptors send a signal to your brain.
Got it. Right.
So there are kind of two classes of odor eliminators. And one truly chemically alters the odor.
Okay.
And the other is what I call cover-up smell. So the cover-up smell essentially just puts so much of another odor in the air that it overwhelms your odor receptors so you can't smell the bad smell anymore. The other kind actually chemically alters it.
Nice. Okay. This is a thing I've definitely wondered about.
So a cover-up would be like a candle or just a good smelling spray with none of the actual absorbers in it.
Right.
The other kind, the odor absorbers, in this case, in the case of Febreze and a lot of other sprays, there's what's known as cyclodextrin.
Okay.
And cyclodextrin is a sugar-like compound, but it makes a ring with a hole in the middle.
Uh-huh.
Kind of like a donut. Or the shape is really, the exact shape is if you take an ice cream cone and you cut off the pointy part at the bottom. So you just have a ring that is larger at the top and smaller at the bottom.
Okay.
That it's open all the way down. And much like soap, the inside of the ring has intermolecular forces that bond with certain types of organic compounds, a kind with no polarity. It's a non-polar bonding.
Okay.
So odors can go and sit in that ring. The intermolecular forces will hold them in place, and then they will not vaporize into the air.
Okay.
So they have chemically altered the ability for these molecules to go into the air. They're held in place there, and the odor is quite literally absorbed into the ring.
Interesting. So the inside is non-polar.
Right.
Okay. And then the outside is polar?
I think the outside is polar, although most of the resources I read talked about the hole on the inside being non-polar, also called hydrophobic.
Right. Got it.
So here's the thing about this. This type of chemistry is actually very, very common. And I can't believe we haven't talked about it yet at this point. This is what's known as host-guest chemistry. So the cyclodextrin is the host, and the odor molecules come and sit inside, and they're the guests.
Got it.
That is used all over the place. In fact, I even took a class on this type of chemistry. It's called supramolecular chemistry. So that's big molecules that will host other things. Not always. Sometimes polymers are classed in with supramolecular, but there's a whole section about host-guest chemistry and supramolecular chemistry. And when I was younger, I did research designing a host molecule that would capture arsenic. They use these to collect ions. There are certain types of molecules that will specifically bond with different sized ions. The cavity will be bigger or smaller to go with different ions. It's used for all kinds of stuff. They can use it in medicines. It's awesome.
Wow. That's crazy. Especially because I think for most of us, hearing the phrase like host-guest chemistry would be most of concern to us whenever we're hosting a party and we want to make sure we have a really good like vibe with our guests.
Were you just holding on to that whole time?
Yeah, I was just like, that's so funny because like you could just write that on a piece of paper and hand it to somebody, and the first way they would interpret it would be about like social chemistry. You know what I mean? Because it's like host and guest.
Well, in my mind, the first place I would go to would be this.
Yeah,
host-guest chemistry.
That's so funny. It'd be like a test to see if somebody is or is not a chemist with one phrase.
Exactly. Sometimes people do that same thing with unionized versus unionized. How do you read that? Which almost works, but I don't know that I ever talk about things being unionized, you know?
Yeah.
But I do talk about host-guest chemistry, so this is a better version of that joke. But nobody would get it except for chemists and people who listen to this podcast.
Yeah.
So in this case, this host-guest chemistry is responsible for eliminating odors by quite literally having a cavity or a hole that perfectly fits in non-polar odor molecules. And this exact same molecule, cyclodextrin, is used not only for odor molecules, but for any non-polar compound. So they're using it right now, testing using it in a polymer to make a filtration system where you can capture non-polar organic molecules that are hanging out and contaminating water.
Oh, wow.
Isn't that cool? So I envision a polymer with these just embedded in it, and you can run it through water and it'll capture and hold in place all those non-polar molecules that shouldn't be in your water.
Yeah, interesting.
So like for oil spills or something, yeah.
Yeah, because water's polar, and then it should be like so perfectly selecting the right things and leaving behind the things that don't matter. Interesting.
Right. And in my textbook that I had from the class, they talk about cyclodextrin in a lot of different places, but sometimes to hold things in place, they'll have a surface. One, they were talking about a gold surface that had cyclodextrin rings all on top of it. Mm-hmm. And then they could use that as an anchor point to hold any kind of molecule with a nonpolar tail that could fit in there. Uh-huh. So the nonpolar tail would come and fit in, and then now you've basically created a surface that has whatever kind of molecule you want sitting on top, or a surface that can capture molecules. It's really cool.
Interesting. That's so weird, dude. That's just kind of crazy.
I know. It's really interesting. I almost would imagine it like a surface covered with tires or something. Mm-hmm. And then there's things that fit just perfectly in the tires. So then you can hold, giant balls on top of the tires or something else that you want to sit. And so you can just cover a layer of a surface in something else or to capture something or whatever, which I think is really cool.
Yeah, dang. Weird, dude. That's so crazy. Kind of feels like a little bit like not chemistry for a second, partly because it feels like almost like tiny physics or something. I don't know what else you call it, but like, because we're talking about like these little things that fit inside these things. And it's like, just kind of weird because it feels, because there's these shapes we're talking about and things that fit in it, it feels a little bit not as much chemistry-y as some of the other topics do. It's like,
yes,
kind of easy to imagine too.
Yes, so easy to imagine, so natural and instinctive.
Yeah, yeah.
You're like, okay, I understand things that fit in other things and stick there, you know? But what you said is important. It's not just about, there's the shape and size like you talked about. So you have to have a cavity or a hole that will fit the molecule, but also then it has to be the right kind of molecule that would interact, because water could go in and out of this and it would not want to bind to it. It would be afraid of those surfaces. It's hydrophobic, Right. So water could move in and out and it would be fine, but something that was nonpolar would move in and be held. Or if something was nonpolar and giant, it might not be able to get into that cavity. And so then it would not be captured either. So you have to look at both of those things when you're looking at host-guest chemistry. Do I have the right type of intermolecular forces, the return of intermolecular forces? And do I have the right size and shape cavity? We have to look at both of those things.
Yeah, yeah.
And I think this type of chemistry is a lot easier to imagine because they use a lot of phrases we understand. Like we know about cavities. We've seen cavities. We know about holes and things. Another type of host-guest interaction is a tweezer. So it has two long arms and can just come and hold it. A different kind of host. Yeah. So it's things that we've seen and it's based off of real life things that we use a lot. It's much easier to grasp than it is to grasp the basics of an atom or the way electrons move. We don't have as many examples of those in real life, but we do have examples of putting something into something else,
Yeah, exactly. Interesting.
So that's it. And it may seem kind of simple that, okay, all that happens is Febreze traps the cyclodextrin in Febreze traps these odor molecules, but that's simple to you because you've been listening to chemistry this whole past year and a half. So you know what intermolecular forces are. So we don't have to talk about those. You know about polarity, all that stuff. So that is kind of your foundations have built up about chemistry to where this topic seems really simple.
Yeah. It really does. But it's also kind of cool because I think thinking about how could something actually not just cover up an odor, but eliminate it in a way. I think I thought, man, that'd be so hard. You'd have to have something that could kind of go in to all these molecules and like change what they are or break them apart. But in this case, it's like, no, we'll like envelop it and keep it from, it still exists inside of this thing, but whenever it enters our nose, our receptors or whatever aren't engaging with the actual odor molecule, so we don't smell it anymore. And go ahead.
I was going to say, I'm not sure if it even gets to our odor receptors. I think it might make it to where it can't vaporize, so it can't even get to our nose.
Oh, there we go. Yeah, so it can't even, so it can't be in the air in the same way and be like a tiny vapor that we can smell. But just that idea that it's doing it that way is kind of cool and sneaky, I guess. It kind of feels like it'd be way harder to have something that goes in and kind of like busts up all of these odor molecules or chemically alters them at the very like breaking apart the atoms or something like that level. But instead of just like covering it up, and like holding it, seems like a really sneaky way to do that, and way easier to wrap my head around. It's like, oh my gosh, that's so perfect that kind of like, what did you say, cyclodextrin?
Yep, cyclodextrin.
That even exists already is like so perfect that someone was like, hey, wait a second, why don't I get these guys over here to do that already just exist in the world? I know,
it's so exciting, so clever. I love chemistry.
So let me sum that up sort of, because I think one way to think about it would be that, and this is probably intentional, the fact that cyclo is in the name of the molecule, cyclodextrin.
Yes.
Like all these little tornadoes are out there, and they only have eyes for the type of molecule that is also nonpolar, like the inside of the cyclone, the inside of a tornado. And so obviously we can harness that specifically to try to get at odor molecules that we know are nonpolar also. Mm-hmm. But really they are just, like any tornado, is just trying to destroy whatever. And in this case, it'd be only nonpolar things. So it could be things that have an odor that we want to get rid of, or things that don't, or could be used to purposefully filter other things out of other stuff. But in general, it's just these little tornadoes that you can unleash onto some nonpolar group of molecules. And if they can fit in there, then you'll be good. For instance, like a tornado can't really do much damage to like a mountain. It's just too big.
Yeah, it's just too big.
It's like kind of like mountains are like, okay, all right, see ya. Like there's just no like no relation at all. But then all of us are like, tornadoes are huge. That's a serious problem, and we're worried about it.
Because we're so small. Yeah. The way I thought about it, that's a good visual image, especially the part about the mountain being too big.
Yeah.
I kind of thought about it like convicts and they're trying to escape or something. And it just is a bunch of people grabbing them and holding them, and they can't go. And they're only looking for convicts. They're not looking for anything else.
Yeah.
And it's just some really big dudes that can grab the people and hold them in place, kind of. And then they can't do any more damage. They're not able to escape and do bad things like make your nose smell bad anymore. They're trapped and held in place, neutralized by someone who's bigger and stronger and looking for them specifically.
Right. That makes more sense, especially because like a tornado, it breaks down because a tornado destroys stuff or just like spins it around and then flings it. So that doesn't really work for our purposes here. But just the idea, the picture came to mind because of the shape of the molecule of like,
yes, that is the perfect shape.
Yeah.
It is very tornado-y.
And it holds it in there because of intermolecular forces. I want to make sure I said each piece of it or whatever. But did I miss anything? What else?
I don't think so. I think that's right. It has to be the right shape to hold something, and it has to have the right kinds of intermolecular forces. And like I said before, we kind of skimmed over that stuff with intermolecular forces, but we talk in depth about this specific type of intermolecular forces on the very first episode on how does soap work. So you can go check that out and learn about intermolecular forces if you're a little bit like, wait, but how does it hold it in there? That's how.
And then we had 3 other like kind of series in a row later that were different types of intermolecular forces in each episode, right?
Yes.
Geckos and whatnot.
So that's it. That's how some odor eliminators work. simply by holding on to those odor molecules and not letting them run away.
Dang, very cool. And then they can't get in the air to be in a vapor form to be smelled by us in the first place.
Right, exactly. And that same type of technology is used in other areas in research a lot already, and they're specifically looking at using that as a way to filter contaminated water sources with nonpolar compounds such as oil spills or other organic molecules that are nonpolar that are in water that shouldn't be.
Yeah, it seems like there could be like a lot of uses for that.
Oh, 100%. There are a lot of uses for this already. So that's really cool and exciting that that same, not only type of technology, but the exact molecule is one that I had learned about and heard about before. And I would be very surprised if host guest chemistry did not come back up again. I'm sure it will because it is so applicable and is in so many places. You jumped right into explaining jam, so I didn't have the opportunity to tease you with a little fun fact or opinion that I have about this. Okay.
Do we still get it, even though I didn't read terms and conditions before I signed up?
Yes, I definitely. You earned it. So, it's about that, not about the fact that I didn't get to tease you. But one of the resources I used, and I use these a lot, is the ACS reaction videos. American Chemical Society has a series of videos about the reactions of chemistry in everyday life. And they pose the question, how do you think you can have odor absorbers that absorb odors that also have a smell in them?
And
I have a theory.
Okay.
But before I give my theory, I want you and everyone to stop and think and try to come up with your best guess. And then I'll tell you what my best guess is. And I didn't find any factual information about this anywhere. So this is just my best guess. But I want you guys to think about it. Use your thinking critically, what I know about chemistry skills to see what you can come up with.
Okay, so I used my imagination brain, and I have just one theory that came to mind that I sort of stuck on. And I think I could maybe try to come up with others if I tried, but here's what really came to mind that I thought seemed the most simple. If you could make the good smell that you're trying to replace the bad smell with, if you could make the good smell molecule be polar.
Yes, that was one of my theories too, is if it's polar, it will not fit in.
Yeah.
It won't stay in.
And it wouldn't even be attracted or whatever, like it wouldn't.
Right. It could come in and pass out and it would be no problem, just like other polar items would.
Yeah.
The other thought is that it might be too big.
Right. Just make it could even be non-polar, but just be too large to fit in the cyclone.
That was my theory. Yes. Is if it's too big, it couldn't fit and it wouldn't have a smell, or if it's polar. I don't know. I've never done smell chemistry. I don't know how to molecularly engineer smell chemistry. I think there are smells that are, or molecules that have a smell, I guess I should say, that are polar. So I would suspect that they either utilize that or they utilize the size or maybe a combination of both depending on what scent they're going for. But that also could make it limiting because if it is a smell they want to have, but it's hard to get in those two categories, that could be a challenge. So that's why people and companies like Febreze hire chemists to work on stuff like that.
Can you imagine if, like, when you looked at the chemistry and you tried to find either some like polar smell molecules that smell good or some smell molecules that are larger, too large to fit into the cyclodextrin? What if, like, the list is kind of a weird hodgepodge of what smells? Like, they're like, okay, so we've got cinnamon, we've got hibiscus, and mint. That's it. That's all that can actually work chemistry wise. And it's just like,
yeah, just like some random ones.
Yeah.
Nobody wants their house to smell like that.
Yeah. It's like, okay, great. We've got cinnamon for like, that works well for like the fall and like Christmas time, holiday time. But it's just like, be funny to see what it'd be like if you had to be limited to only a few flavors and learning these like laws of nature that only allow you to replace with certain smells. And it's like, man, dang it. Okay. Hope everybody likes mint.
I guess this is where we're at. Yeah.
Yeah.
That's funny. Great. Well, I'm glad that you thought through that and came up with something that was really exciting. And I thought it was fun on the video. They posed that question and never answered it. So I wanted us to spend some time thinking about it.
I think that's great. Do you think they're planning to, or did they just want to get people thinking?
I think they just wanted to get people thinking. And they didn't go as much into the host guest chemistry stuff. So I think it might have been a little bit harder from that episode to come up with it. But I thought it was a really fun thing to do. So
dang, that's cool. I like that. Like a little chemistry riddle, you know?
Yeah. Solving mysteries.
Is it time to talk about something happy that happened during our weeks?
Yeah, absolutely. It's time. Do you have something happy you want to share?
Yes, I do. A small thing. So I, as you and the listeners, most of whom probably know, I love coffee and I roast coffee just for myself and a few friends, not like crazy legit, but I'm a home coffee roaster. And I have had a coffee for like several months now that I bought a lot of, like 40 pounds of. And just this past week got low enough on that coffee where it was time to start looking at different coffees again.
Ooh.
Just like everything, fruits, and vegetables, there's seasons for coffee, and for different parts of the world, that season's different. And so at any time you look, and also just the fact that things have to ship from, different countries to the US and stuff. So anytime you look, you never know what coffees might be available. It's kind of a surprise. Sometimes it's a bad surprise because you're looking for something kind of specific and it's not going to be available. But it's just always changing all the time. So any of the places I look to buy coffee from, the coffees they have available are always going to be different, varying from season to season. And so I went through the process, which is sometimes stressful, but other times really fun. This time it was fun to look for what coffee I was going to order next for myself and the people who I roast for, kind of some neighbors and friends and stuff. And I got some I'm pretty excited about. One that I've liked in the past that was available again, that I got again.
That's exciting. Yeah, you're like, oh, I really love this, but it was out of stock, so now it's back.
Yes, now it's back. And then I got a coffee that is then I got a coffee that's a little bit unusual. It's from Colombia, but it's what's called honey processed, which is
interesting.
A little different than, it's just not the normal way for Colombian coffees to be processed. They leave some of the fruit on while it's drying in the sun. And it has, that's normally a process you might see in parts of Africa, but not necessarily in Colombia. So that's pretty interesting. And then the last one is a decaf coffee that's decaffeinated through a slightly different process than I normally buy. And it's called mountain water processed. And so I'm pretty excited to see how those go. I don't drink a lot of decaf, but two people who I roast for do. And so I'm just kind of interested to see how those turn out. And
how exciting. You've got some experiments kind of going. You're trying new things, testing stuff out.
Yep. So I'm pumped about that. And I've had this coffee for this other one that I'm almost out of for like a long time. So it's also just kind of cool to move on and drink something else. So how about you? What's your week been like? What's something happy that's happened?
Well, my week has been kind of crazy, actually, because this past weekend we had my mom's memorial. And due to COVID, and my sister lives out of town, so there was hurricanes to be contended with where she lives, which kind of impacted us, Because of all that, it's been really hard to find a place where we can safely honor my mom and a time. And so it finally all came together where we were able to honor her this past weekend. And that was really sweet and special. It was very hectic and overwhelming and a lot of things to prepare for. But one thing I got to do that I had really wanted to do was sometimes people will make little garden cakes out of fondant vegetables. And I saw that maybe 2 years ago, and I was like, I have to make this for my mom's birthday. And then she passed away before I got the chance to do it. So that was what I wanted to do for her memorial with my family afterwards, is have that cake that I had always planned to make for her, sort of as an opportunity to make one more cake for my mom. And so she grew in vegetables in her garden. So I specifically picked vegetables that she grew and made them out of fondant, which was something new that I haven't done before. And it was really, really fun. And so we had that. And some of my former students, they're now friends of mine, Kristen and James, I'm going to give them a shout out, made us a full meal to eat after the memorial. Wow. And it was so nice because I had no plan. I texted my family, I've got a plan for breakfast. I have a dessert afterwards, and I have no plan for dinner. So do not ask me what I am doing because I don't have a plan.
Yeah.
And they just took care of it. They made us a delicious brisket, mac and cheese. It was so nice. So
that's way cool.
That's
a tough meal to make too. It's not like just like hey, we threw a casserole together. It's like that's some time and some energy.
Oh, yeah. And they made cinnamon rolls for breakfast the next day. It was really so thoughtful and exactly what we needed, met a physical need that we had not had the capacity to think about. And so it was just really sweet and really special. So those are some highlights to something that was kind of bittersweet, some silver linings and some cool things that came out of it. So
that's awesome. Yeah, that's cool. That's really cool. Dang.
So that was my week. It was pretty hectic, pretty crazy, kind of challenging at some points, but also really nice to have some of those happier things. I think because some time has passed, it's easier to maybe spend some more time celebrating and less time mourning. So it was kind of beautiful in that way.
Yeah, I think that's awesome.
All right. Well, thanks so much for also Jam was there at the memorial safely, social distantly with a mask on. So thanks for coming to that, Jam.
Absolutely.
And thanks for coming here today to learn about how odors work. Odor absorbers, I guess, work.
Dude, thanks for teaching us. Very fascinating topic. And these topics like this are some of the coolest ones come from you guys. So if you have ideas of chemistry in your everyday life, things you think might have a chemistry explanation to some mystery that occurs, please let us know. We love to hear your ideas. Reach out to us on Twitter, Instagram, Facebook, or Gmail at Chem for Your Life. That's Chem, F-O-R, Your Life, to share your thoughts and ideas. If you'd like to help us keep our show going and contribute to cover the cost of making it, go to ko-fi.com/chemforyourlife and donate the cost of a cup of coffee. If you're not able to donate, you can still help us by subscribing to your favorite podcast app and rating and writing a review on Apple Podcasts. That also helps us to be able to share chemistry with even more people.
This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson. References for this episode can be found in our show notes or on our website. Jam Robinson is our producer, and we'd like to give a special thanks to A. Hefner and N. Newell, who reviewed this episode.